In this lesson, we'll be looking at relative age dating and unconformities. In looking at a set of principles, or relative age principles, we can put a group of stratigraphic units or events in order based on their relative position to one another. We're going to do this by using stratigraphic laws or principles of relative age dating. Stratigraphic laws or principles of relative age dating are used to help establish a sequence of events. Stratigraphy is the study of strata or sedimentary layers. The first three stratigraphic laws or principles were established by Nicholas Steno from 1638 to 1686, who through personal observations noted the three principles. Steno's first principle is the principle of superposition, as shown below, which states that when sediment is undisturbed, the oldest layer is on the bottom and the youngest layer is on the top. So looking at this image here, the oldest layer, or layer A, has to be older than layer B because it's on the bottom. The next oldest unit would then be B, followed by C. So we can put these in sequence from oldest to youngest based on their position. A being the oldest, B being the next youngest, and C being the youngest of the sedimentary rocks shown. Steno's next principle was the principle of original horizontality, which states deposition of sediments essentially occur in horizontal layers. Therefore, sequence of sedimentary rock layers that are steeply inclined from the horizontal must have been tilted after deposition and lithification. So looking here, these follow the original horizontality. Layer A, followed by layer B, followed by layer C, are all laid down in a horizontal fashion. If they had any way been tilted or tipped upward, then we know that an event had interfered with the samples after they were deposited. Steno's next principle is the principle of lateral continuity. In this principle, it states that sediment extends laterally in all directions until it thins, or pinches out, or terminates against the edge of a depositional basin. What we see here is a cross-section of sediments, A, B, and C, that have actually terminated against the edge of this depositional basin. A is the oldest, followed by B on top, being the next youngest, and then C being the youngest. Now let's move into some other principles. These principles were not stated by Steno, but followed later. There's the principle of cross-cutting relationships. This holds that an igneous intrusion or fault must be younger than the rock it intrudes or it cuts across. If we look at the unit over here with F, E, and D, and then an intrusion, a dike crossing it, X. For F, E, and D to be older than F, E, and D have to be older than X. They had to exist before X could cut them. This is like looking at a loaf of bread. A loaf of bread is older than the cuts that run through it. The bread existed before it was cut. Therefore, the bread is older than the slices that cut through it. So, in placing these in order, we can put F as the oldest because it's on the bottom, superposition, followed by E, and then D, and then finally X, which cuts all three. We could have the same thing happen with a fault. So if we look at this image over here, we see a fault cutting a sequence of units. We can see that K, H, and J have all been offset from one another on either side, indicating a fault or a slice. This would be like a bread being sliced and then slightly pushing the slices down to the side. They offset from one another. Same thing, the units that are on the bottom, which are K, have to be the oldest, followed then by H, then J, and then finally the fault, which is G. And in this case, the fault is a reversed fault. We know this by looking at the slant here. If we looked at this slice or this fault like it was a child's slide, children will slide down the slide. That's the normal direction to go. But when we look at this one as just like we would with a child's slide, we can see that the H unit, instead of sliding down, it's actually slid up in the reversed manner. So this is a reversed fault. Another principle is the principle of inclusions, which holds that inclusions or fragments in a rock unit are older than the rock unit itself. For example, granite inclusions in sandstone are older than the sandstone. So if we look here, we have unit X down below. This is going to be a conglomerate, and we see pieces of that same unit as inclusions in unit Y. These inclusions are older than the unit they're in. Think of raisin bread. The raisins had to exist before they were baked into the bread. The raisins are older than the bread itself. This is the same principle here. These inclusions had to exist before they got placed into unit Y. Therefore, these inclusions from X are actually older than Y. Another principle of relative age dating would be the principle of fossil succession, which holds that fossils, and especially groups of assemblages of fossils, succeed one another through time in a regular and predictable order. Now that we know the principles of relative age dating, let's look at a few other things like unconformities. Unconformities represent periods of non-deposition, erosion, or both, on a surface that results in a missing time or hiatus in the rock record. The term unconformity encompasses three types of these surfaces, one being a disconformity, then an angular unconformity, and a nonconformity. Let's look at a disconformity. A disconformity is a surface of erosion or non-deposition that is separating younger from older rocks, both of which are parallel with one another. So looking here, we see this jagged line. Oftentimes in a sketch of a cross-section of rock, we'll either see a very solid line indicating a disconformity, or we may see a kind of misshapen line or jagged line. This would represent a place of erosion or missing time. So in these units, following the original horizontality and superposition from Steno's principles, we know that the oldest has to be on the bottom, which is W, followed by X. But then we run into this erosional surface where we have missing time. This is the S. This erosion takes place at S before we have the deposition of Z. So when we look at the units, we have W, X, then the S, which is a disconformity. Remember, this is missing time in between parallel beds. So we have a set of parallel beds here where we have missing time, so it's a disconformity, and then followed on top by Z, which is the youngest unit shown. Another type of unconformity is an angular unconformity. Angular unconformities are going to be when we have an erosional surface on a tilted or folded strata over which younger strata were deposited. The strata below the unconformity or unconformable surface generally dip more steeply than those above, producing an angular relationship. So if we look at this image down here, we see that we have a set of units that are all coming in at an angle. We have unit X, unit V, and unit C, all coming in at an angle. What's happened is these units were originally laid down in a horizontal manner, but then we probably had some folding. So kind of if you think about it and kind of follow my pen mark here, my mouse, we come around, these probably folded up just like you would take a piece of paper and fold it into a curved shape. Once they were curved or folded, then erosion occurred, and that's what this point A is, and it eroded off the top of the curve, followed by deposition of a new sediment, H, on top. So coming down here, we have X. If we were to try to put this back into its position, and we try to straighten this back out, then we would see X coming down to the bottom, followed by V, and then C. Well, once they were deposited, they had to be tilted or folded, so this information goes into the line. Then they were eroded, which resulted in the unconformity A, and that unconformity is an angular unconformity because the units are at an angle, finally followed by the youngest unit, the last unit deposited, which is H. Our last type of unconformity is a nonconformity. This is where we see an erosional surface cut into metamorphic or igneous rocks that is then covered by sedimentary rock. It closely resembles an intrusive igneous contact with sedimentary rocks. The principle of inclusions is helpful in determining whether the relationship between the underlying igneous rock and the overlying sedimentary rock is the result of an intrusion or a result of an erosion. We can see here we have this igneous rock body, and we have our nonconformity here with a sedimentary rock, in this case a sandstone, following over the top. And then finally on top of that our unit S, or our shale. So that means that following superposition, A is our oldest rock, it's on the bottom, followed by that nonconformity, that contact zone, erosional zone between that igneous rock and that sedimentary rock, which is U, followed by unit B being deposited, and finally unit S being deposited. Well, let's apply this on a larger scale. We come over here, we see a cross section where we've got several things going on. We want to put all this information onto the lines to the side, indicating the oldest to the youngest. Also, with those units F, O, and P, we want to name them or identify what they are. So if we come over here and we look, we see that we have unit V with unit Z, B, and W. They've actually all been folded with one another. If you were to imagine unfolding these units, V, Z, B, and W, we would see that V is on the bottom. So V has to be the oldest, followed by Z, then B, and then W. After these were deposited, we see that the top of the units have been actually eroded away. The top of the curve is missing on B and W. It's been eroded away. So we have unit F here. And if we look at how these are coming in to the unit above, we see that it's angular. So we have an angular unconformity at F. So F would be the next one. On top of F, we have our limestone, M, that's being deposited. And this limestone M is actually being crossed by K. K is also crossing the units V, Z, B, and W. Therefore, K has to be younger than these units, because it's cross-cutting. So we'd follow this with K. After K, we see that K has been eroded as well as M at the top by O. So this is an erosional surface, and we have missing time, so this would be a disconformity. This is then overlain by A, which has been crossed by R, cross-cutting relations. R is crossing all the units including A. And then it's being cut off by P. P is between horizontal beds again. So P is an erosional surface where we have missing time or a hiatus in time. So this is a disconformity. And then lastly, E. So we want to fill those in. We have V first down at the bottom. We have V down here, followed by Z. Z's right on top of it, followed by B and W. So B and W. and then F is cutting across and cutting off the top of that unit, and it's an angular unconformity. We have then laid on top of that M, which is being cut by K. K is also cutting all the units below it. So K is younger than all the units that lie below it, so it lies on top. This is a dike. We then have we then have O coming in here, and this is between parallel sedimentary units. This is just missing time and erosional surface, so O is a disconformity, followed by A on top of that. A is then also being cut by R. Because it's being cut by R, R has to be younger than A, and it's younger than all the units that precede it down below. R is then being cut by P. It's been cut off. And P is another disconformity. We see that the beds are parallel to one another, and so it's cutting off. Lastly, deposited on top is E. You're going to follow the same procedure with the diagrams in your lab manual as well. So this concludes the lesson on relative age dating and unconformities.